Alright, hi everybody. So I just want to finish up with you a few things related to organic chemistry, some of the more advanced organic reactions, one of them being the oxidation of alcohols. This is generally not seen on the Regents exam, but when you take a more advanced chemistry course like IB chemistry, they do talk about this oxidation of alcohols. I'm going to introduce it to you here. For oxidation of alcohols, if you have a primary alcohol, remember that's an alcohol where you have an hydroxyl group, the functional group for the alcohol on the end. And then if we were to oxidize this, usually we'll use something like a dichromate reactant. And this will oxidize this alcohol, and what it will actually oxidize it to is an aldehyde. And then if we further oxidize this with more Cr2O7 2-, we could actually further oxidize it to a carboxylic acid. And so this is the oxidation of alcohols. Primary alcohols will oxidize to where they form an aldehyde or a carboxylic acid. A secondary alcohol, when we oxidize a secondary alcohol using the same dichromate, we will actually get a ketone. And this is my ketone right here. Now it doesn't oxidize further. You won't make an ester from this. You'll just stop at a ketone. Now if we had a tertiary alcohol, those are generally non-reactive, so those won't oxidize at all. Okay. So this is fractional distillation of hydrocarbons. And so usually what will happen is you'll start off with some kind of crude mixture of different hydrocarbons, crude oil really, and you'll heat that up. And that will transform them or change them into a gas. It'll vaporize them. And the vapor will rise up the fractionating column. And what we'll see is that the really light hydrocarbons, those will stay gases even below 40. A lot of those light hydrocarbons like butane and propane, those will remain a gas even at less than 40. But as we look at the heavier ones like pentane, these will start to condense when their temperatures drop to between 40 and 200. And the ones between 12 and 16, they'll start to condense when their temperature is cools to 200 and 300, and so on. So we can see that some of them will actually stay as gases even with temperatures that are as liquids, even when they're temperatures that are greater than 370. And so this allows you to separate out all of the hydrocarbons based on their boiling point. It's just like any other distillation. But this is a really complex mixture that requires a high level of fractionating distillation. This way you can really separate out the hydrocarbons. Now once you have a mixture of 1 to 4, like methane through butane, then you can further refine those and isolate them further. So let's talk a little bit about some other experimental techniques. There are 3 that are really covered in IB. One of them is called infrared spectroscopy. And what infrared spectroscopy allows you to do is it allows you to identify the functional groups of compounds by determining how the compound absorbs IR light. And so what they end up doing is they end up taking a sample of your compound and they pass it through this pretty complicated machine, and they see how your sample will absorb IR light. Now what's nice about infrared spectroscopy is there is this huge sort of database of different patterns that people have sort of accumulated through the years. And so if your compound has an OH group in it from an alcohol, then it's easy to compare it to compounds that have OH and say, yes, my compound has a hydroxyl group in it. If it has a carboxylic acid, a carboxyl group, you can compare it to other compounds that have carboxyl groups. Now, infrared spectroscopy on its own will not tell you the entire, molecular structure of your compound. It's nice to also be able to tell the fragments and the masses of the fragments of your compound. And this is an approach called mass spectrometry. Now, with mass spec, what they will do is they will take a sample of your compound and they will turn it into a gas. They'll vaporize it. They will then use a ionizing radiation to ionize your sample. And they do that basically by removing an electron. Once they ionize your sample, they will measure the mass of fragments created. And what they'll see is that your sample, it will have its whole intact fragment. Let's say that you have something like methanol. Methanol's total mass would be 15, 16, and 16 would be 32. And so when you pass this through a mass spec machine, on the detector, you will receive a fragment that is about 32 grams. But also, the compound can be split into fragments like CH3. And this CH3, it will be having a mass of only 15 grams. And you could also create the OH fragment, and that fragment will have a mass of 17 grams. And so you could piece these together. So you could piece together the 15-gram fragment and the 17-gram fragment, plus you'll also have the full, what they call the molecular ion, and you'll have those and you'll be able to see how large the compound is. And again, just like with IR, mass spec, they have a whole library of different fragments, so they understand. If you're a scientist working on this, you're like, yeah, I know what fragments are supposed to be created. The last technique that's used is something called NMR, nuclear magnetic resonance. You know this as an MRI machine that's used to, look at structures in, a living organism, but they didn't like the term nuclear. People were scared away from that. But really it's NMR, nuclear magnetic resonance. And what NMR does is it looks at what they call environment of hydrogen atoms. And from this, they can see how many hydrogen atoms are in a particular environment, and from there they can piece together what the molecule looks like. For example, if I were to give you something like this, 2-propanol. Well, there's hydrogens attached to all these carbons, and there's also a hydrogen attached to the oxygen. So really there's 3 environments. There's the environments where you have the hydrogens attached to the N carbons. There's the environment where you have the H attached to the O. And there's the third environment where the H is attached to the C. And so a scientist looking at data from an NMR machine would see that there would be 3 different, what they call peaks, with varying sizes. There would be a peak that would be the height of 6 hydrogens. There would be a peak that would be 1 hydrogen, and another peak that would be 1 hydrogen. The difference is that the 2 1 hydrogen peaks from the one attached to the oxygen and the one attached to the carbon would have different placements on the graph. And again, there is a library of known structures. And so scientists can use what they get from their unknown compound and compare it to a known structure. And from there, they can figure out, oh yeah, okay, this is what my structure should look like. So next year we'll do more with this. If you take IB chemistry will actually go into detail and look at all the graphs. You'll see what an IR spec graph looks like, what a mass spec graph looks like, and what an NMR graph looks like, and you'll be asked to do some interpretation of it. Alright, so this is organic chemistry. The major focus of your exam is going to be on naming the compounds, identifying functional groups, and types of reactions. That's what we're going to do for our exam. So, good luck, and thanks for watching.